Okay, welcome. Thank you for attending, everyone, this evening. It's a great turnout. How many lectures have we had so far this year? What are we on? I can't remember what number we're on, but we're well into our lecture season, and we have a fantastic presentation for you tonight. So let me give you a little background. I first met Shawn Brixey back in the late 20th century at UC Berkeley. And Shawn was the chair of the New Media program there and director of New Media Research. And he had just come out of the Media Lab and Center for Advanced Visual Studies at MIT, and he was doing some remarkable work. At that time, I had been invited to exhibit work at the Cooper Hewitt Museum in New York City as part of the Smithsonian's first design triennial. And I convinced the museum that it'd be better for it'd be more appropriate, actually, for us to create a new work of design for the museum rather than just put up old work. So they agreed to that, and I immediately invited Shawn to join the project because we faced a particular challenge in the design. We had to figure out how to convert liquid into light and then set it to the beat of a human heart. So Shawn rose to the occasion. He figured out how to do that. Don't try that at home. It's dangerous. But he rose to the challenge, and the resultant work, which is entitled Liquescence, was a hit for the show. So Shawn has continued to take on remarkable challenges and create more memorable work. I'll just give you the title of a few of some of his recent projects. Aurora, Aqua Echo, Alchemia, Eon, Epicycle, Glacier Clone, Photon Voice, Sky Chasm, and Secret Agents. Here are a few reasons why I think Shawn is remarkable and his work is remarkable. He gives measure to the unmeasurable. He makes art out of matter and energy, and he makes art relevant to life. His work is truly transdisciplinary. We use that word quite often lately, but not everyone lives up to it. And he crosses borders between art and science, between design and engineering, and technology and medicine. He also has several lessons to offer for everyone tonight, especially artists and designers. And those are: pursue your interests in the world with passion, understand those interests with intensity, and reach out to other disciplines in order to pioneer a vastly more creative and unique perspective on the world and in your own work. And Shawn's work has been wildly and widely published and exhibited throughout the world. He's lectured extensively. He just gave me a list of the cities and countries he's got on his docket for the next month or so. In addition to his work, he's also held several academic positions, most recently at the University of Washington as a Jones Endowed Chair in Arts and Sciences. He's received numerous awards, including a Rockefeller Foundation Fellowship, not easy to come by, and also recognition by the National Endowment for the Arts. This is not Shawn's first time in Michigan. Back in 1989, he was a Leonardo Fellow at the University of Michigan. And he was also visiting artist at Cranbrook Academy just down the road. So please welcome him to LTU, Shawn Brixey.
Thank you, Ralph. Thank you, everyone. Thank you, Ralph. It's a delight to reconnect. It's been a few years since Ralph and I have had as much of a conversation as we've had today. Can everyone hear me? Is this all right? Do I need to pull a little closer? Yes, better? Okay, I am born and raised in the Midwest, so I can bark it out pretty loud, but I'll try to rely on this as much as possible. I won't show slides tonight, actually, from Liquescence because I didn't want it to turn into a Shawn and Ralph love fest. So I figured that I would actually start in another place. But I am delighted to be here. I did my postdoc at Michigan, spent a year or two at Cranbrook, and really loved my time there. My wife is from Michigan, so we have a tendency to float in and out of the state pretty regularly. But this is the first time I've been on LTU campus, having known about it for many, many years. And so I'm delighted to meet everyone. What I thought I would do is make sure that we cover the important stuff. that I'm here as a part of the AIA Continuing Education Series, and to make sure that people know sort of the take-homes tonight. Some of what I'm going to talk about is the hybrid relationships that are being developed across design, engineering, art, architecture, computer science, et cetera, that are creating these sort of new hybrid practices. We'll explore some key distinctions between simulation and emulation. I don't like dyads. I am much more fluid about constructing kind of conceptual problems that way, problematics, but this is an important one to kind of figure out. We'll also talk about visual synthesis, oral synthesis, algorithmic processes, sensing and control systems, and telematics, which are the way in which we break down our disciplines now. Then I'll use some case studies. Ralph listed a few of them. One's for the European Union that I just came back from Portugal. Another one's for the Berkeley Art Museum, and another one's for the Winter Olympics, et cetera. And then hopefully we'll have some conversation about how these kinds of relationships meet in various forms and in various projects, and how they're sort of inflecting a new kind of hybrid practice, a new hybrid curriculum, and actually a new hybrid rigor for the disciplines of design, art, architecture, engineering, and as they're starting to fuse. The way I like to kind of approach this, if my slides will work. Yeah, there we go. I'll walk you through a brief academic overview, a little deeper dive than what Ralph gave you to give you kind of a context. And it's not just my resume. It will show how an artist can actually end up doing work for the National Science Foundation for a year, and then end up doing IEEE, and then end up working in design, end up working in medicine. Then I'll give you a little bit of personal history. We'll dive pretty deep on the research praxis side. And if we do have time, I'd set my scale at 75 minutes. I know some of you may not have the time to do that. I'll also kind of pull back to determine how many people are falling asleep. And I'll actually show some student work, which is really exciting, and I get really excited to talk about their work as well. I've held a number of academic positions, did my grad degree at the Media Lab, was at Cranbrook and at Ann Arbor, held my first faculty line at the University of Kentucky, and actually founded their digital media program. Went on to the University of Washington, so I spent a lot of time founding programs, primarily because I have a hybrid background. Met Ralph at UC Berkeley during that period, came back to the University of Washington to build a new program called DX Arts, which I'll talk about a little bit. It has a slightly different flavor and look and feel from what most university campuses have. And then retired from the directorship 3 years ago to take on an endowed chair, which allows me to travel and do exciting work with various universities and various governmental agencies, et cetera. I'm actually not as prodigious as my as my studio colleagues. They'll have 5, 6, 7, 8, 10 shows a year. I typically do one about every 3 years. As you'll see, the work is fairly complicated. It takes a lot of laboratory research, a lot of collaboration, a lot of iterative design process, then funding, installing, and then lots of documentation. But I do pick the venues pretty carefully. Documenta, the Yeshiva, MIT Museum, the Winter Olympics in Nagano, Japan, the Schneider in Oregon, and recently the EU. I just came back from Norway. I'm working on a project up there too, which is about 1,000 miles north of Svalbard, which is about 200 miles from the North Pole. So I'll give you a little brief snapshot of some of those as well. And also for an artist, I really pride myself getting awards and distinctions and resources well outside of the fields that typically we're trained in, and whether it's design or engineering, but all the way from the Corporation for Public Broadcasting to Leica and 3M to Hughes Aircraft to the National Science Foundation, Rockefeller, et cetera, Apple Computer. My parents were radio and stage performers. My father was a Broadway actor, and my mother was a symphony cellist before World War II. After the war, when television hit in the US, they actually didn't have taped recordings. Everything was live, and so you needed people who were fundamentally trained at a really expert level at doing live performance. So after the war, My parents were tapped to be producers of the Grand Ole Opry. Some of you will remember some of these people. This is going to be Hank Williams. This is what television looked like in those days. I grew up next to Patsy Cline and Johnny Cash and had a really interesting childhood. My parents were then moved from the Grand Ole Opry to their sister institution called the Ozark Jubilee. And the Ozark Jubilee is in Branson, Missouri. For those of you who have traveled there and enjoy it, thank you. For those of you who travel there and don't or were drugged there by your parents, I'm sorry for all of the damage that they inflicted on the nation. Branson is sort of like Las Vegas, but country western Las Vegas, and the country western stars figured that instead of traveling and dying in seedy motels or airplane crashes or bus crashes, they would actually have you come to them. But the interesting thing about the Ozark Jubilee was that it was for crossover music. So you don't see too many cowboy boots. You might see a bolo, or there's not even a cowboy hat. This was the early sort of version of MTV. This is when the crossover music used special effects, multi-camera. They didn't use synthesizers, but they used various kinds of electronics. So it was a really hip regional show that was, of course, broadcast nationally. I show this not to kind of give you, all of my background, but to give you a picture like this. So as a kid, when my parents were producing television, I really didn't see them as having anything to do with movies or music stars or doing film. But in essence, what I saw was that my parents would nightly encode people's images, their dreams, their imagination, their spirit, and their ideas, and beam it magically through some sort of electromagnetic force thousands of miles away, and have that teleported to people's houses and have it decoded by a box. And depending on how big your box was as a kid was depending on how big the people arrived in your home. So I really thought my parents were teleporting people, and I got really excited about this idea. I never really thought of it as having anything to do with video. So I grew up on the floor of a TV studio. Like most of you, how many of you, raise your hands in here, sort of fall in the category of being a designer? Okay, that's a lot of you. Artists, studio practitioners, any hybrids in here? There's a few of you, yeah, thankfully. Architects? Good. Engineers? Did we pull any of you in? Yeah, great. A lot of times when you have, let's say, a proclivity for doing something well, and I'll just take drawing, for example, a youngster will be encouraged, whether it's by a mentor, or by a grandparent, or even by a sibling, to kind of continue on. So I happen to be able to draw and paint very well, so they encouraged me to go to art school. And when I went to art school, I went to the Kansas City Art Institute. It was really considered one of the best schools during that period. And this have been probably the early 80s. We often called it art boot camp. A lot of the students that came out of there have gone on to have very, very successful careers. But given kind of my background, and maybe I was a little bit of a smarty pants, if you could draw and paint well, or if you could do the assignments well, but you had never really understood how to dig down inside yet, the faculty had a way to deal with those kinds of mavericks. I think we can use that now 4 years after it was worn out. They would take you and put you in a yellow school bus, about 12 or 15 of you who didn't quite fit in, and they would drive you 200 miles into western Kansas, and they would drop you at 10 to 20 mile increments by yourself. And they would give you a giant bag of food and a big box full of art supplies. And they would say, if you want to be a painter, make a perfect line. And if you want to be a sculptor, make a perfect moment. And then they would come back anywhere from 6 to 12 hours later before sunset, and they would critique your work. And if you did something interesting, you would stay in art school. And if you did something boring, they would kick you out. So a little different than it is today. So being really sure that I was good at everything, I decided to take a long nap, because most of us know when we're in college in a place like this, you live on caffeine, a lot of contact high from all of your colleagues who are just as energized as you are, and no sleep. And the very first chance you have to not be around people, you take a nap. But unfortunately, I fell asleep for about maybe 10 hours. Blazing hot sun in Kansas, woke up with a scalding sunburn on one side of my face, heart racing. I thought I was going to die. Had an anxiety attack, I assume that's what it was. And I thought for sure they were going to like ship me off and I would basically be a footnote in history. But then I just had this feeling. I had this gut feeling. So I dug a hole in the ground. They give you an army shovel so you can you've got this kit with you. So I dug a hole in the ground and I took the big 3-gallon jug of water that they gave me and I quickly took a palette knife and I cut the top off. I laid it down in there and I made sort of like a small pond or a moat. Then I grabbed 6 inches of wheat chaff and I cut it off and I split it down the middle, flayed it open as fast as I could and I laid it flat on top. And then I took a long darning needle, about a 3-incher with a magnet that I had, and then I magnetized it as fast as I could and I laid it on top of the surface of the water. Does anybody know what I did when I did that? Yeah, all of you know that. I created a compass. But about 30 minutes after I completed this, and I really wasn't sure what I was doing, the bus rolls up, everybody piles out, big cloud of dust, all the faculty come and they stare into this hole and nobody says anything. I'm thinking, oh my gosh, I'm absolutely out of here. So they rustle everybody back on and they kind of pull my neck and insist that I sit in the back. But I started to realize what they realized, that if you know anything about Faraday lines and magnetism, that the compass actually draws a perfect line, circumscribes the globe with unerring accuracy 24,000 miles. And just to top it off, because of all the Faraday lines, it actually infers all potential future lines, which are themselves perfect. So I had created a perfect line. And if you want to double down, if you know anything about tensor fields, right? Then what you have as a tensor field is the magnetic field around the Earth. I don't want to get into a whiteboard conversation about it, but a tensor field really is always in a state of becoming. It never is. It's a perfect moment, right? Exactly. It's in a state of flux, a permanent state of flux. So I had sort of pulled the sword from the stone, and I assume they had used this set of exercises for 30 years for recalcitrant art students. And so rather than having a moment of hubris and arrogance when I went back to school and everybody high-fived and maybe bought me a beer, I actually really asked myself, how did I do that? What was going on? What was the process behind that? Could I get underneath the hood of that, and could I do that again? Could I build a practice around that? Could I rely on that? And so to rely on that, I actually was taken out of school, still was in the Kansas City Art Institute, but was apprenticed to a gentleman named Dale Eldred. And I traveled all over the world with him to build massive hybrid art, engineering, architecture projects. This one's for the Nelson-Atkins Museum in Kansas City. Huge batteries of mirrors that would be aligned for a precision moment for 3 minutes a day, where beams of sunlight would come into the museum. They would kill all the lights with rare Caravaggios and elaborate paintings everywhere, sculptures. And you would have these beams of light, sort of not unlike the Great Pyramids of Cheops, coming in and illuminating these spaces with these time incident projects. This is holographic diffraction grating. Of course, this is the 1980s, so you can't go to the party store and buy this stuff. This is really rare. It's only made in the most exotic science and military laboratories. So to get huge quantities of this and to turn it into projects was something pretty interesting. We also built batteries of tens of thousands of 16-foot 2x12s and dropped them in on axis lines relating to the position of the Earth at particular times. And so as you drove along the big boulevards in Kansas City, you would see these blazes of light that would sort of ignite the path and would only last for a few minutes depending on when you were coming in and where you were going. It really does look a lot like this. This is not Photoshop. We didn't have it in the 1980s. You had to actually write your own algorithms if you were going to do anything similar to that. Working with Dale was somewhat interesting because if you worked for him, you kind of gave up your own personality. Everyone, even the women, we all had our head shaved. We were given 4 outfits, paramilitary outfits. We were given a winter outfit, a summer outfit, a fall, and a spring. Wherever you sat down in a restaurant, if you had a table of 20, he would just pick out one of everything, and wherever it came out, that's what you got to eat. It was a pretty wild ride, but a very interesting proving ground. And I realized as a part of my arts practice that at a fundamental point that creating images and objects that represented the interpretation of my imagination would never fulfill what it is that I actually wanted to do, which was to create the thing itself And I'll talk about that more, about the difference between a simulation and emulation. But that's the kernel of the difference between a simulation and an emulation. And so luckily, at the Kansas City Art Institute at that time, the head of the humanities program was a retired physicist. I worked my tail off and had me do quite a bit of physics and engineering, and said that I was very good at it. And I was also starting to illuminate new ideas that he had not seen before. And so he encouraged me to go to the Media Lab at MIT, which I did. And in the early days, MIT only allowed 5 of us in at a time. The 5 of us were required to be excellent scientists and engineers. And then on the side, we were allowed to do something exploratory, speculative, that we could call whatever we wanted to. MIT at that time also had CAVS, and the head of it was Juri Kepish. Juri Kepish was the lighting engineer for Moholy-Nagy. We can kind of walk back historically, and you can find that the history of it is pretty powerful. But the Media Lab was a very nascent creature at that point. Now there's 200 doctoral students at the Media Lab, and every different flavor that you can imagine. My area of focus when I was in graduate school was actually on holography, rainbow holography. Almost every one of you have a wallet in your pocket or in your purse tonight, and you're going to have a rainbow hologram. It's going to be on your credit card, or it's going to be on your passport. And all of those were the ones that I developed when I was in grad school. So I also luckily worked with Otto Pina, who was a very interesting designer that came out of Group Zero. Group Zero is a group of German artists, designers, architects that came out of Germany after World War II. And his area of interest was in inflatables and in performance. And I also, one of my grad mentors was Harold Edgerton, or Doc, as we lovingly called him. Most of you have all seen these photographs. And so that's sort of I'll say the history of my background. I'm going to dive into some projects and watch the time very carefully. The first project I'm actually going to show you will be computer-generated models, so you can kind of get the conceptual rubric. And then I'll dive into real documentation of all of the other ones. This project is called Instruments of Material Poetry. And this is a 500 million candle powered light source. It emits a beam of light focused through a series of lenses into an evacuated flask. The flask's vacuum is so precise, or it's so strong, that it's 4 × 10⁻⁴ torr. So even if I took all of you up into the space shuttle and we grabbed a big bucket of vacuum, it'd be about 4 times better vacuum than you would get in deep space. As the light goes through here, it's reflected off of a bunch of surfaces that I'll talk about in a minute, through optical engines, and converted from light into electricity, and electricity into sound. So if I took all of you out into the desert and we made a pair of giant aluminum foil gloves that was 1 square mile, and somehow we could all magically kind of lean down and lift them and have it sort of levitated, and there was no clouds in the sky and the sun was beaming down on it, how much do you think that the light falling on that 1 square mile would weigh? Trick question.
10 pounds at least.
No, photons don't have any mass, right? So they don't weigh anything. However, you are right, because when a photon strikes an object, it can actually impart its kinetic momentum to it. So it's very strange. Doesn't make sense. They don't weigh anything, but when they hit something, they can actually give the force to it. So 1 square mile weighs about 6 pounds. And what I have done is created about 0.003 of a gram of radiation pressure from this very, very powerful light source. Inside of this flask, however, are graphite particles, the same graphite that you'll see as we walk down the hallways here of people's drawings. I did lots of elaborate drawings and theoretical writings and collected the particles and put them in the bottom of this flask. In the bottom, there's a piezoelectric transducer, which is a loudspeaker, really, really small, and it gives a massive mechanical shock, and it knocks all the particles up into this vacuum, and the light slams into it, forcing the particles to start to spin, and they spin violently just like a planet does on an axis, and they increase in mass through inertia. They form a flat oblate disk, just like a galaxy does. That's time-lapse photo. And I encode my voice actually into the light source. So now the light is not just simply levitating the objects, but the light is getting brighter and darker, and the amount of gravitational force that's created, in essence, the artificial gravity created by the light, is increasing or decreasing the speed of the rotation. As the particles spin, They bounce light off of them, and the bounce light actually has voice encoded into it, but because the spin rate is changing because of the force that's placed on it, the voice coming out of it is Doppler shifted, the same way that a fire engine coming towards you would have the pitch increased, and a fire engine going away has the pitch going down. So this is a still photograph, not a time-lapse photograph, of millions of particles, each one spinning on their own axis. I'm from Missouri, which is a show me state, so I will show you video. This is not all smoke and mirrors. I've shown in too many museums for it to be that. But I showed this particular slide because this is a binary system, which is very similar to what we see in deep space. And this is its axis of rotation, and the cluster's axis of rotation is right there. Remember, there's a pure vacuum, so there's no gas in there. I'm not stirring this up from heat. This is true particle levitation. And so it's a project that really is just the interaction of photons with electrons and matter. And this is, as they start to form their flat oblate disk, you'll see a projection of the field of view down here. I think this is about 5 millimeters at this point. Is this real time? That's real time. Yeah, that's a 5 millimeter field of view. So the edge here to the edge there is 5 millimeters. That's going to be about 2 millimeters. And as we start zooming in here, yeah, I think I put in a shorter video than normal. As we start zooming in, the space starts emptying out because what seems really dense from far away is actually very, very empty. I will give time for quite a few questions, but I want to blaze through some projects for you so that we can cover some solid ground. The project that I just finished in Guimarães, Portugal, or Guimarães, was for the Capital of Culture. In the US, I think we have a really difficult time sort of thinking through the problematic of global warming, climate change. Even our recent election is sort of a referendum on a lot of these debates. But the Europeans are very, very clear and very, very nervous. And they had seen a project that I had done for the Winter Olympics where I took the blood and urine from athletes to create snowflakes that could never exist in nature. When you're a child, you're told that no two snowflakes are alike, right? And your parents are absolutely right about that. But, and the reason that they are is that if two of us were snowflakes and we were falling somewhere in Michigan and we were near each other, snowflake is nothing more than a story. But the story is so complex that it's really a precise atomic recording of the history of its fall. And if we could pull the threads of that story out, you would see just every possible force, the temperature logarithm, the surface tension, the heat dissipation, et cetera. So it's a very compound, complex story. So if you step back and think about it other than an impossibly complex story, but just simply a system for telling stories, I approached the European Union with sort of a variation on the project that I had done for the Winter Olympics, where we would take ultra-pure water, and ultra-pure water can no longer freeze till minus 41 degrees below 0 Celsius. It's had all of its impurities removed. So you can drop its temperature way beyond any logical sort of metric that we think that water is going to freeze by. We use it in semiconductor construction and in biotechnology. And if you keep it at minus 40 degrees Celsius, it's in permanent suspended animation. It's going through a lot of random permutations looking for some kind of similar structure that it can go from a liquid to a solid in, but there's no way to go through a phase change. But if you dope that water with a substance that has a very high epitaxy or atomic similarity at the temperature that it's at, it'll instantly freeze. And in that instant freezing, it'll actually record whatever has been placed into it. So I'm actually able to record stories. So what we did in Portugal was actually take core samples from 20,000 years ago, the last glacial maximum where ice had covered northern Europe all the way down to Portugal, and I cloned the glacier that was there 20,000 years ago. So the object itself is not 20,000 years old, it's 20,000 years ago. And we're looking at a little thumbnail, and I'll show you what a crystal looks like once it is frozen. And it doesn't just stay there, it actually migrates over time. The reason that the colors are so brilliant is that the ultra-pure water and the ancient ice do not have the absolute perfect epitaxy. It's about 99.9%. And because of that, there's a little tiny bit of lattice distortion, so as light passes through that, and polarized light is able to give you all of the various colors that are produced based on the amount of force that the lattice is being reshaped by. I'm trying to simplify it a bit. This is the space in Portugal. It's at Fabrica ASA, which is where they made most of the fabrics for Southern Europe, everything from automobiles to the jeans that you wear. But they mothballed it a few years ago, and the EU came in and spent quite a bit of money to turn it into an art, design, architecture, and engineering showcase. The gallery that I showed it in, there's about a 50,000 square foot gallery. And you can see sort of some of the pieces that are constructed as a part of what I'm getting ready to build. These are backlit panels, super high intensity LED panels that can be dropped to 60 degrees below 0 Celsius. Most panels of this type, if you drop them even colder than -20, they'll shatter. They've got tiny laser etched grooves so that they're evenly illuminated the way that your laptop is. But we designed a way to silk screen it so that the grooves don't give any kind of surface for it to crack from. You can see the massive cooling system. Everything inside of here has been chilled. And a lot of the projects relate to sort of similar issues. The exhibition was called Emergencies, and it deals with everything from the emergencies in our economies and our ideas and our society to our environment. There's a special freezer that's brought in, and I'm building the light panels to be installed. Here are the ice crystal cells that are coming from neem, and they are taken from about a mile deep, and they are aged at roughly 18,000 and 20,000 years ago. Here are the light panels installed inside of the freezer. Each one of them is on a special bar with a motor because with sort of fixed monocular vision, the way that a video camera would see it, we don't see it with binocular vision the way that a human eye does. And so the panels actually are allowed to softly rotate over time so that the viewer who can see it live online or can actually see it in the space of the museum can see the crystals from multiple angles without having to move. Even little things inside, big freezers like this with objects that are set up in sort of the arrays that they are have a tendency to create zones of where the air won't cool down or where it will heat up. So there's anti-cavitating fans, all kinds of electronics inside. This is part of the larger exhibition. They took spools of the last wool that was made by the plant many, many years ago and created these massive structures and then placed various kinds of plants that will climb on them. So by the end of the exhibition, the space is this giant organic living tendrils everywhere. It's been sort of reconsumed by nature. The gallery that they placed me in was somewhat interesting. I'm in the air cooling or air handling facility. So there is air that's being pulled across here. And while there is still some noise, they have these really interesting vanes that are shaped a bit like aircraft wings, slightly tapered, and huge series of industrial fans. So as you're standing there, you have this massive airflow. The airflow of the entire building, freezing cold, is pulling by you. Yet, however, you don't feel like wind is blowing. You just feel physically like you're moving in space and in time. There's the HD video camera going out and the ice crystals as they are growing inside. This is what they look like. And yes, not that you would want to think that you'd probably be able to make these as no two can be alike, but we could take chip samples from there and actually clone those. And make very, very similar pieces over and over. These are the same crystals, but just from two slightly different views. A video for you. This is about 12 inches wide by 8 inches high. And some areas which seem like there's not much going on. When we put the charge in, right, the small glacier sample, it blows down rapidly. It sounds like popcorn, bam, just like that. If we had a swimming pool that was chilled below freezing, right, and it was ultra pure, and all of us were in Tyvek suits and class 4 respirators and no contamination, and we had made a snowflake of one of the students or a colleague that had contaminated, and we walked out over the diving board and dropped it into the water. It would freeze instantly, not through the traditional process that you might see in a refrigerator or freezer at home. Lots of people came. And it was interesting to find that often you would see in the space, because the space itself was both telepresent outside and physically projected, you would often find individuals who would, I'll just say, use the space for varying purposes. This is another artist who recorded the animals in shelters that were dying. And the video images that you see here are the heat that's slowly dissipating out of their lifeless bodies. I'm going to watch my time. And this project's Altamira. And maybe when you were a young kid, maybe even now, I know I did as a young kid, you would press your hands on your eyes. And as you do that, slowly you're going to start to see phosphenes. And those are mechanical phosphenes. What's happening is sodium and potassium ions are being liberated by the pressure. You actually probably saw it in the womb before you were born. And that is run down the optic nerve, and the brain sort of takes that stochastic information and generally tries to create legible imagery from it. I was fascinated by that and studied a lot of the scientists who had worked on that, including Max Knoll, who invented the electron microscope in the 1930s. But a lot of the science dead-ended in the 1930s. It was resurrected sort of in the psychedelic era between the late 60s and the early 70s, but was never really moved into any therapeutic space, was never moved into a more rigorous science. And so I started studying this, and I became fascinated at ways to produce the same phenomena, but not through an electrical device or not through mechanical pressure, but through maybe something in nature, through a system that we were long entangled with, but maybe we had sort of grown out of or forgotten. Something that's really present in my work and starts to be reflected in projects like this, and you'll see in a second what I've done. This is the Very Large Array telescope that we're using radio signals to create the project. I was at MIT walking the halls much the way I was today at LTU, and I had done years of analysis of everything from plants to brainwaves to you name it, and nothing really produced that unique signature the way that you can with your hands, or if we just simply use a function generator with like a sawtooth or a sine wave, etc. But when I was walking down the hall of the astronomy department at MIT, out of the corner of my eye, I saw basically a kind of analog image of what normally is done computationally, but an analog image of the information that's coming out of a pulsar. And certain classes of pulsars have a periodicity and actually a signature inside of that pulse pattern that precisely mimics the function that would be necessary to produce the phosphenes. So I got very excited, and I called my friends at MIT to see if we could get some recordings of particular pulsars. And they sent me ones from the Crab Nebula. And we wired up a device very similar to what looks like an iPhone. But instead of a set of headphones, we actually wire them to galvanic electrodes that set on either of your temples and on your occiput back here. And we take the signal from the pulsar and we input that as a very, very low electrical current. If any of you suffer from migraines like I do, the current that we need to stimulate that's very, very low. A normal person might only need 1 volt at maybe 500 milliamps, which is almost nothing. You can hold a D-cell battery in your hand and actually get more than that. And the idea that you could hold something in your hand and have a work of art that in and of itself grounded itself in who you are now, but actually spoke to something that was anywhere between 10 million to 25 million years ago, and at vast scales that are so far outside of operational awareness, we might as well imagine that it's fiction. And what we end up finding is that these pulsars produce images in the mind's eye that look like this. I'll show you a video in a second. And for me, the beauty of a project like this, and it's not for self-praise, it really has to do with the idea that sort of philosophically, theoretically, I approach my practice is that humans are not 100-year biological vessels. We are that. All of us will live roughly 100 years. But we are million-year creatures embedded in a billion-year process. And so how does a designer, an artist, an engineer, someone who's involved in a hybrid practice began to explore what it means to make a work of art, to make an experiential design experience that is in contact with who we are, who we were, and who we will become, all simultaneously woven together. And not in a theoretical sense, but in a very concrete and real and visceral sense. So the reason I'm showing you these, I'm going to show you this in a minute, is that this is a work of art that can only exist in the mind's eye once we wire you up. It's not that we would see it totally differently. We could talk about it and say, oh yeah, I saw the pink, I saw this, I saw that. But it's not something that we can ever have as a poster, or we can't go to a gallery and see it. It's always going to be completely internal to the person who's perceiving it. We could get into some very thorny and exciting philosophical debates around ideas like that, but I just want to plow through these projects to let you know sort of the terrain that I cover. The lights are up a little bit, and I won't ask them to be turned down. But in general, this is what a multiplex series of stars, multiple stars, look like as they're being piped into your head, sort of via wetware. Back to a similar project with the ice, and I'm only going to touch on this really, really quickly. This is a similar project to the one in the EU, but this one's much bigger. The ice core samples are from 1 million years ago. And the project being done is for the University of Alaska Museum of the North. And you can sort of imagine each one of these as a sort of a Jurassic Park freeze frame from a time-lapse movie that's 1 million years old. There are 600 plus ice crystal clones, each one of them with special rear illumination, all kinds of elaborate fabrication processes. Each one of them costs probably at least twice that of a large screen television that you could buy at the local electronics store. There's also a special iPad app that we're building. And the iPad app will allow anyone who's actually not there to be there. And one thing that we're really excited about is generally on tablets, you use sort of a haptic gesture for increasing or decreasing the scale of view with an object. But we're actually developing it to have natural haptic motion, which means if the project's 360 feet long, you physically walk 360 feet to see the whole thing, which is a lot more interesting, right? If I want to sit in an airplane or in a chair and sort of move my fingers like that, certainly there's a view into a space. But humans are very special creatures. If the space is 35 feet long, we can calibrate it for that. But we're really approaching it as a one-to-one relationship. But the ultra interesting thing is if you want to get closer to it, you just walk closer to it, and it gets bigger. So we're very excited because it allows the project to be calibrated for multiple spaces and multiple time zones, multiple locations, which always refers back to sort of I'll just say I don't want to call it a polemic, but some of the conversation around global warming, climate change, et cetera. The ice crystals that are 1 million years old look a little different than they do when they're 20,000 years. It's not just precisely because of the contamination, but the lattices are really compressed. When we pull them out, they have to relax over weeks of time. And as they sort of stretch out, sort of the epitaxy looks a little different. And these are much bigger crystals. I think these are 24 inches. So these are full-sized, full prototypes. And this is exactly what it looks like some psychedelic, mind-blowing acid trip. It's more like holograms than anything else, which would make sense because of what I did my grad degree in. Because as you move around them, it's not just the stereo separation, but you're seeing sort of you're seeing the crystal from multiple points of view simultaneously. I'm going to rifle through these pretty quickly so that we can get on to some student work and make sure that I've got time for questions and answers. This is a project called EON. I received the Rockefeller for this and also the Hellman Award, which is an award that the University of California gives for distinction in research. This is a 1,000 milliliter glass flask. Think of it as like a vase, but a really thick glass vase that's really, really precise. And on top of it are ultra high energy transducers that emit a sound field inside of a glass of water. And the sound field is in the shape of an hourglass or an X like this. And the sound field is so intense that if you stuck your hand in there without the water, it would blow your hand right off. But it would cauterize it in the same moment so you wouldn't bleed to death. So there's good news.
Rock on.
Rock on. So what we do is we send an electrical current that blasts apart the hydrogen and oxygen and produces a bubble at the center of this glass cylinder and inside of the water. And for those of you who had any sort of science or engineering background, we're producing sonoluminescence. We're producing a star in a jar or light that's caused by cavitation of liquids and sound in really, really, really compressed spaces. The best scientists, however, know that they can do this for picoseconds. They've been able to do it for 80 years, but they don't fundamentally still know how or why this happens. So I'm very interested in kind of approaching these liminal spaces between us being able to do things but not really knowing where, why, or how it's happening. But generally what we do in the sciences is we do this for a brief second, bam, and then we record it with street cameras and other instrumentation, and we study that data for a long time to understand what's going on. But because my parents were television producers, I had this interesting idea, why can't we do this 365 days a year, 24 hours a day, and actually use a subcarrier and allow anyone who can type on a keyboard in a Romance language, English, or Japanese and have their voice converted into ultrasound, which is a sound field that creates the bubble, which then creates the light that comes out and is recorded by microscopes, converted from light into electricity and electricity into sound. This is probably a good time to talk about simulation and emulation once I finish up here. If we put this light source behind a prism, you would actually see a spectrum, right, when you look at it. And normally what you would see is absorption lines or emission lines, depending on which direction we're doing it. And that would tell us sort of what the chemical makeup is of this light. But the beauty of this light is that it's a black body spectrum, which means it's light coming from a place that's not made up primarily of hydrogen and oxygen. There's no absorption or emission lines. Either way that you record it. So the light's coming from nowhere, we know where it's coming from. So it's important to realize that, let's say, some of you may have parents that work doing robotic surgery, right? You've got your parent who goes into a space, pulls on, dons a helmet and gloves, and is in a physical three-dimensional space, but extrudes themselves into two-dimensional space to operate on somebody who's not where they are, right? And in spaces that go from 3D to 2D back into 3D. And they are in real locations. They're just remote from their true location. We have rovers on Mars right now, which is a real space, but it's just so far away it might as well be imaginary. It's so far removed from our operational awareness that it might as well be imaginary. So rather than doing computer graphics, and I'm not dissing anybody who does, sort of my background, my passion, and not wanting to make objects and images that represent the interpretation of my ideas, but actually fundamentally teaching my students and myself the basic principles of the way that the universe operates, and allows them to inflect their ideas into their organizing principles. We often call this system aesthetic. That means if I took a photograph of you and we put it under an electron microscope, at a certain level you would just blow away, right? The symbolic reference to you would no longer be there, and it would just be made up of paper pulp and the materials that are there. But artists, scientists, designers, architects, engineers who work inside of system aesthetic means that there's no level that we cannot observe that work, sort of that the fundamental operating principles, the idea, our symbols, our relationships are always fundamentally there. There's not a level that we can't observe it. Then it also becomes there's no level that we're not responsible at, right, that we can step away from. because it is about decisions, it is about outcomes, it is about all of those things. I'll show you a video real quick. And this is about 50,000 times a second slowed down. The radius of collapse goes from visible to almost invisible. Then a blast or a burst of light comes out, and that burst of light is then detected by our system and then converted from light into electricity and electricity into sound. I'm going to watch my time. It's about 5 till 7, and I've just haven't even gotten into student work yet. Hello? I think this one doesn't want to stop. Is everybody doing okay? Interested? Go a little farther? Show some student work? Okay. This will be the last project that I'll show, and I won't show a video of it. But I was invited to do a project with the Human Genome scientists who were trying to solve it in those days. The Human Genome was a pretty daring undertaking, and it was not something that we had a bird's eye view from. There wasn't a legend, and we were just sort of assembling a language or syntax out of. And so when I was commissioned to do this project, I wanted to create a project that in a way was as complex as the Human Genome project. So what we decided on was to build a giant telerobotic maze that could be operated at a distance by anyone in the world. And anyone in the world would be allowed to log in and basically move a video camera across a three-dimensional space that houses a human thumbprint. But the human thumbprint itself is like a giant maze. And at every point in that maze, you're allowed to drop a meme, and the meme can be graphics, video, text, audio file. And those sort of breadcrumbs, those information genes are used to sequence the space. And the view that you get if you come into the maze space online is just this simple view here with a browser that allows you to have sort of cardinal directions for movement. And then you can excavate in a z-axis infinite numbers of memes that have been left in 4 different layers: audio, text, graphic, cinema. And there is a sort of a mathematical algorithm that roams the maze. So every time you drop a meme over time, it's just like going home to visit your parents. The city's not the same, the streets aren't the same, the houses have been painted. And so all of the data inside of this space, just like in epigenetic expression of our genes, I'm a twin, and so my twin looks a little different than I do. Maybe they drank a little more orange juice. Maybe they had a little more sun. Maybe they drove faster on a motorcycle. We're not exactly sure what causes the gene expression. But as millions of people would go into this maze space and leave all of these sort of archaeological layers, they would also mutate in time. There was a real true solution. It was simply a maze, but a maze at a point of view that's so limited, like the Human Genome Project, with such simplicity and complexity required, in essence, thousands, if not hundreds of thousands of people forming sort of social organisms to sequence or to solve the maze space. There were at least 6 bounties on it by computer science programs from the best Research One universities, and they could never solve it. But it's imminently solvable. It just requires humans to solve it. Computers are not smart enough at this point. There's a nice video on my website that will walk you through it and tell you more about the project. I'll show you DxArts quickly and then some student work, and we'll call it an evening. I'll watch my clock here. Okay. So I was hired up from UC Berkeley to come to UW and build a new hybrid program. We call it DxArts. It's housed in Raitt Hall on campus at UW. It's a very beautiful campus, lots of neo-Gothic architecture. We went in and blew out all the spaces, created space specifically for the kind of work that we're doing. What DxArts does is primarily support artists, designers, architects engineers, dancers, physicists, everyone who's working at sort of the edge of their discipline and crossing over into the allied disciplines and is wanting to do exploratory research, speculative research. That's primarily what we do. We have a unique undergraduate program. The undergrads are allowed 5 years instead of 4. The state allows this. They have a special degree designation. Most of the undergrads are triple majors, so imagine astrobiology, dance, and architecture. While that doesn't make any sense when I list it out like that, many of you will have hybrid interests and you know how to inflect and how to make meaning out of those, which is very important. One of the things we do at the undergraduate level is in your 6th quarter, which you've been there a year and a half, you're immediately bumped to graduate level courses. You no longer spend time at the 200, 300, or 400 level. You go into a doctoral laboratory and all undergrads are required to do original research. That means you are working as fast and as hard as you can towards things, creating new knowledge, new ideas that we haven't seen before. We have really nice spaces, every kind of space, a lot like the spaces that Ralph showed me here, all the way from CNC labs. Every undergraduate is taught how to print and make flexible and rigid circuit boards. Nobody doesn't do that. All of the projects come with embedded systems. We have CNC shops, wood shops, giant robotic control systems for camera motion. You basically name it and DxArts has it. In fact, we have the largest CNC footprint on campus, more than mechanical engineering, and they often come to our labs to use our equipment, and we're really excited about that. We do have a PhD program as well. And many of the PhD students themselves coming in have expertise in one field, meaning they're a world leader in a specialized discipline, but they want to move or migrate into another field. And generally, there's no program like that that would allow them to move, let's say, from being a concert pianist to being a roboticist. That just doesn't exist. And so we've created special curriculum and program for them. The undergrads do really, really well. 100% of those who apply get into grad school. No one's rejected, which is pretty amazing. And they go to really remarkable schools. Some of these that I've asterisked are actually, they are doing dual grad degrees in their studio practice, whether it's architecture, design, and they're also doing law degrees because the research that they did as an undergrad created new IP, and that IP has not fully been sort of understood. And so they're actually becoming an expert, not only in their own field of creative practice, but in all of the legal ramifications of the creative practice that they've developed. Lots of them go on to work for really interesting corporations, as well as do independent studio work. I'll stand over here and rifle through some of these. A lot of you have seen 3D movies, but we're actually working on what's called stereo depth modulation. That means by altering the interocular distance of the cameras, either in real time or on computers, we're able to create synthetic or three-dimensional space that cannot ever be built in the real world, but humans can perceive it. I only brought 2 stereo pairs here because we actually would have had to bring in like a 4K projector and active LCD glasses. And to show it requires a massive space. We did this in Poland. That's 90 feet wide, probably 120 feet tall. Lots and lots of computers, special holophonic sound. We're doing wavefret synthesis. So we're actually creating sound not from recordings, but the interaction of various pressure waves that reproduce the sound holophonically in space. Computer-controlled lighting. And this was done for, I think, about 12 or 1,500 people at a festival in Poland. We do a lot of mechatronic and robotic work. This is photopaque and it's like a kind of, the laser's not working, oh, it's going in the opposite direction. Various types of robotic systems that allow for projections to have varying kinds of opacity. All the students make and build their own instrumentarium, machine all of their own parts. This is a prototype. It's a real-time interactive mechatronic robotic installation where hundreds of these are being made. And the videos will show up with varying layers of transparency as they sort of work their way through abstract and experimental narratives. I don't think we really have time to go out on the internet, so I'll go through a project that I think will be easier to kind of work on. I'll turn my sound up. Do we have sound? Well, you just have to believe me. It's really interesting to listen to. Imagine now in the future that we go to a film and the computer graphics and the special effects are not pre-rendered. We use live sensing and control systems, and in this case, these are birds where we have microphones that are set up all over the city, and we're listening to them in various parks and in public spaces and on beaches, and the animations are rendering themselves live on the fly based on the sound input that's coming from the various locations. We just switched to a beach, and these would be seagulls. I've got my sound ported in over here. I've got it. Yeah, I've got it in. Yeah, it's up. Yeah, the audio should be out just fine. Don't worry about it. I think we are covering a lot already. And this is RFID sensing and control systems with phase array antennas. Basically, we have dance performers that have RFID tags and RFID antennas on them. And as they move through space, they actually create the sound and the computer graphic scenography live on the fly. So instead of the performers chasing the scenography or the click track for the musicians that are playing, it's in fact their bodies, their relationships, their proximities, which are generating all of the sound and the scenography. So if there's a particular phrase that a group of dancers or performers that are allowed by the choreographer to do and repeat them, on Saturday they may do 8 gestures, but on Sunday they may do 12. Basically because they're improvising it gives them the chance to really recreate the performance exactly as they want at that moment. We did a project where we took over 40 closed-circuit cameras in Cambridge, England. In the UK, there are roughly 1 camera per 14 people. It's the most observed populace in the world. We switched out those cameras with high-quality cinema cameras, but we ran them through a box that is basically a neural network. And that special computer that they're run into had only been shown the film Blow Up by Antonioni based on Cortázar's short story. So what's happening is that these cameras and the computer are looking for people who are doing things exactly like in the movie. And what's beautiful is that you may live here on campus and see that you're sitting next to somebody that you don't know. You may only see them in a classroom like this. But what was happening is that people in Cambridge were realizing that picking up dog stuff and drinking coffee and going out and taking photographs and waiting for the bus, their life was being transcribed through the epic grammar and syntax of cinema and then being reprojected at night in downtown in the UK. And so they began modifying their behaviors to not simply just arrive as talent, but to create this larger idea of community in space, but all inflected through this larger and more epic language and grammar and syntax of cinema. Again, this would be another computer-realized piece that we would have to go out for. Generally, what we're doing is we're doing data mining on your cell phones. We have films that never see the light of day through a camera, but they exist entirely through network devices. Some of them have bank accounts. Other ones use reverse Bayesian filters. Every one of you use one every day on your email where you try to keep spam out. We can flip that over and actually have, let's say, an email account become obsessed with certain kinds of information and go looking for it. And then we use rule-based polygon rendering to create a kind of a synesthetic film that gives the nature of the film almost a sense of self-awareness. It's very uncanny to watch. Some people find it uncomfortable to watch because it begins to take on human-like characteristics and behaviors as it goes through it. Other things that we do is simple motion capture, but the motion capture is generated gesturally to create the groundwork for monumental sculptures. The same gestural control we use for editing video. So all of a sudden we're using or not using, but simply the students in DX Arts, almost all of them are required to have at least 1/4, if not 2, of dance, if not simply human movement, because a lot of that sort of somatic awareness of the body and the body embedded in space and in systems is really important. I would often say to a science colleague that if you take a 15-week dance class, you're actually taking 15,000 years of human movement. And there's a lot of knowledge to be understood there. And artists, designers, architects, engineers in general, we have a pretty good idea of that. We do a lot of teleporting. We're doing ultrasound projects where we're recording cities like areas in Seoul, Korea, where we can present that sound not simply as a recording, but through holophonic sound, so that when you're standing there in the spaces that are made, let's say we could go home to somebody's apartment or go home for the holidays and record someone's living room with a Christmas tree in it, with all the lights off. Even when you go home to visit your family or another kind of holiday experience, when something's shifted and you go home and you immediately know if you've got bags of groceries in the kitchen but you've left the lights off, you can sort of hear the difference. We're able to transmit those kinds of spaces so accurately that you feel that the space that you're in is not the space that you're in, but it's somewhere else. Lots of ultrasound work. These are ultrasonic gloves that allow for the performers to steer certain sounds that you might not hear. One of you may hear, but another one may not hear. It's like voices in your head. We do a lot of time remapping and time sculpting. This particular project's a dance project where the light elements that the dancers are wearing are real time, and the dark elements are actually sort of algorithmically anticipated. That means that the video that's being created is not really being recorded by a camera, but being speculated by an algorithm on the computer side to generate sort of a set of dance relationships as the performers are moving through space, participating with them, but also anticipating moves that they may or may never not make. Again, these all have really nice sound, and since we're not able to do it, I'll just scrub these. Most of you have had at least a little bit of art studio background and history, and you know, all are familiar, of course, with the cubists who wanted to be able to basically render images from every point in space at every point in time. And they were required, because of the systems that they used, to always do it from a fixed point in space, but inflect the idea of multiple points in space, even though they were painting from one particular area. And so we've created a software called Tesseract, which allows us to take, let's say, every frame in a movie, and we stack them on top of each other like a three-dimensional cube, and we use a data glove, and we go out and we pick individual pixels from the beginning, middle, and the end of the movie, and then we bring them all forward to form a single frame, right? And then we can compose different moments of time across there, so a person's shadow arrives before they do, their hands touch before the body ever enters, etc. We increase the aspect ratio of the films. These are just experimental shorts, because the amount of time that's on view, if we had a normal 3x4 or even 16x9, it's not enough sort of time domain for us to be able to observe. So these are typically like 32x9, and there are films being made like this where you're basically watching the beginning, middle, and end all simultaneously and excavating relationships over time. A lot of 3D work, motion capture work, so we're doing live motion capture, particle animation that's presented to, of course, a live audience. This is a group of choreographers and dancers that are floating in space on bungee cords. Large transparent screens, much bigger than this, are rolling through space, and the images projected on there are motion captured from their body movement, using a markerless system that allows us to create particle animations that in essence are reflections of the kind of collective movement that all of them are doing together. So instead of a fixed rigid screen where we're looking at fixed three-dimensional objects, you have three-dimensional objects interacting with virtual three-dimensional objects, creating a new kind of space. I showed this one to Ralph a few minutes ago. One of our graduate students was given an award in Louisiana to go down after Katrina and to do a project based on the devastation. And she was really interested in a lot of this kind of 19th century flocked wallpaper, which was full of mold and just strewn everywhere. And so she worked in the laboratory to create undifferentiated plant cells, which then would be allowed to go through a kind of permutation growth so that the wallpaper would grow from this nascent state all the way through sort of the luxurious version of possibly what it had been all the way through to death and decay. And it takes a couple of weeks to do that. This is a little heady to kind of get into, but a lot of the students and myself also do work for the Navy, National Science Foundation, and we were approached by Popular Science, who were doing a design problem to create a care package for a community in need in the 21st century. And we had a feeling that the winner was always going to be somebody who focused on humans, because we're pretty homocentric, and so we went the opposite direction and we focused on marine mammals. And we used the ultrasound work that I showed you earlier from the Eon piece and reverse engineered that to create basically Bose noise cancellation robotic AUVs for underwater mammals. And so the Navy would come in and drop, basically use a drone, and they would drop in robotic AUVs. The AUVs would swim with the pods. The pods would have incoming sonar, which produces sonoluminescence in their ears, right? And a deaf marine mammal, right, is a blind when they can't see. And so what the pod does is it listens for incoming sonar, and it produces a 180-degree phase pulse based on the incoming sonar and repels the sonar, cloaking them and allowing for the marine mammals to, of course, swim unfettered and, of course, to live on. And then we use the same drone to pick up the AUVs. We put the mission accomplished in there on purpose, just in case the irony is. We do a lot of motion picture work. And this, again, these all have phenomenal soundtracks that would be great to listen to, but we do a combination of robotic, mechatronic, and special algorithmic processes to do animations for all different kinds of communities, whether it's an art community or a cinema community, engineering. But these same technologies get used in multiple ways. Other filmmakers come and want us to do the art direction or develop a new look and feel, new technology for them. This is Guy Madden, this is Brand on the Brain. And this is not done through software. We built elaborate optical lensing systems to give him a look and feel of a kind of an excavated historical cinematic moment that no longer exists. And since we don't have audio, most of you know these bands like the Killers. They come to DX Arts and we do all of their rock videos for them. I don't teach my students to do rock videos, but often when you're doing speculative design research like this, we have really cool ideas that are often not incubated in the halcyon environments of Southern California. So we do the videos for, let's see here. Yeah, we do the Killers, we do Polar. We also do Queens of the Stone Age, Hoobastank, Hot Autism, lots and lots and lots of various bands. Anyway, I had to rush a little bit at the end. I'm trying to be prescient of everyone's time. It's exactly 7:18. I went 18 minutes over. And I really appreciate your time. I do want to make sure that you know that there's opportunity for questions. I'd love to answer those. And I've taught for 25 years, so nothing, don't be shy. Just ask straight away.
Yeah, and in fact, I've got the mic here, so
great.
whoever wants to ask a question, I'll bring the mic over.
I covered a huge amount of territory.
Edward, I'm waiting for you to ask a question. You're still formulating.
Hi, I have a question that relates to global warming,
Sure.
which you covered. I recently seen an interview with someone who works with the EU, and he was talking about the third industrial revolution. I don't know if you're familiar with that at all.
Yes, but you can explain it. for
Okay,
your
it's
colleagues.
like the first two industrial revolutions had to do with like the discovery of oil, and then the other one was like electricity. So the third one is going to be with mixing the internet with like green technology and a way to fuse those two together to deliver the energy via the internet. So I'm wondering if any of your design work had to do with any of those areas at all.
That's a really interesting question. I was talking with Ralph because we both, LTU and a place like UW are somewhat different. We're a Research One university, and so it seems like we have infinite amounts of money, which we don't. But we are the first-ranked federally funded university in America, so we get more money than most. But that's dedicated to very particular kinds of research. So you might see that my work is not terribly practical. It looks more like the theoretical stuff, but in fact, it's really truly embodied. But we're now designing classes where the students actually have limited technology, typically internet-based technology, smartphone, simple apps either that they make or that they buy, and social media sites, and then we have them approach really significant problems of the future, but with extremely limited resources. Now, from my own point of view, being a professor, while I'm being practical with them at the same time, I'm also encouraging them to think very, very differently about their approaches. So I would say to you, the internet is not simply a place where you and I do our online banking, where we buy clothes from Banana Republic and we read the most salacious headlines of the last day. In fact, I think of the internet as the lowest level implementation of humans trying to be omniscient, which is to be in contact with everything simultaneously. When I was talking about simulation and emulation, let's say that you and I had $50 billion and we built the most impressive, full immersive, full force feedback cave system, right, projection system in the world, and we decided to make an apple. And that you and I go in there and we can feel it. It has all different kinds of surfaces. It's really familiar to us. But we could also go to Meijer down the road and buy a plastic apple for $5. And it has a higher order of implementation than a $50 billion simulation because it's an emulation. It resides in the same phenomenological space that you and I do. And so when I look at things like the internet, while I may teach a class that uses now, instead of extraordinary resources, we actually limit them to address particular problems, I'm always having my students think very conceptually different about something as simple as the internet. Instead of just taking it like a utility and saying it's there, let's use it, let's solve problems. It's like, no. Before we start using it, let's think more completely, more holistically, which is why I sort of have a problem with the dyad of simulation, which is things that represent pictures, objects, etc., and emulation, which are indistinguishable from things themselves. So while we do teach drawing, perceptual drawing, we teach a lot of stuff that they do in art school, our undergrads and our doctoral students as well, chemistry, biology, computer science, physics. They have this very different kind of road that they take because we always want them observing that world and questioning those things instead of just simply saying we're using the internet. Then what is the internet really made of and what is it for? Why have humans created that? And I would propose to you that we're not just 100-year biological vessels, we're million-year creatures embedded in a billion-year process, and we're making the internet so that we can, at a low level of implementation, figure out what it means over time to be sort of in contact with all of this stuff. Humans are going to inherit every single space, every scale in the universe if we don't kill ourselves first, right? You've got moms and dads going to work in very small spaces where their hands don't fit. And we've got other people who are working millions of miles away on planets. And that's just the tip of the iceberg. And so we have to figure out that deeper meaning, not just simply of climate change so that we can keep going, but really sort of why we're doing these things, why we've created systems like that, and what their reflections are. This building is really not a building, it's your brain, right? It's your brain externalized, maybe someone else's brain who came before you. But in essence, not getting too philosophical, you can kind of see how I would approach that. So we would address your problem directly, as you said, but we would also think very philosophically about it and ask questions about the systems that we've made. We're all walking around with screens right now. We carry them with us. We're talking to people, but we always have a screen present. What does that really mean? Why are we doing that?
Did he answer your question?
Sort of.
That was a joke. Other questions? Edward.
Yeah, oh.
My question, I think, is kind of a stupid question.
Good. Those are the best.
Well, it's because it's like a question that you would get asked by obnoxious teachers.
Are you going to ask me what is art?
Maybe.
Okay.
But more in the context of the fact that normally with that question, that comes about kind of trying to get students to expand their definition beyond just kind of the historical precedents for something. But since your goal is to be expanding at the frontiers of something, how do you orient yourself within kind of the context of the rest of the world? Or is it simply that do you strive not to do that, to resist it actively, to then be more open to different approaches?
So what you're asking me is what we, in essence, prepare our graduate students, our doctoral students to do, which is to frame the question. The most important thing is to be able to frame the question. So often in a general exam, the faculty frame a question pretending to be the doctoral student in 25 years. So for example, this may sound like a dithyrambic thread, but I will come back. We had a doctoral student who started working in haptic cinema. That means when you can feel the movie with your hands. So we actually created a general exam where you had to create a silent haptic movie, meaning a silent film with no sound that you could only feel, right, for 10 people. That's never been done before. And so students need to be thinking like that. How do I do these sort of things? What are the kinds of experiences? And at the end of that, when the engineers were there and they were writing down notes, I had everybody stop because all their hands were still moving. And I said, I think you're having a haptic after image. And then no one had ever contextualized that before. And so they start writing it down, and immediately they want to participate with our group, right? Because we're framing questions in really, really novel ways, really interesting ways that I do believe discover new kinds of knowledge and create documentation of what it means to be human in really radically new and enduring terms. So back to your primary question, is that if I frame the question as you would ask me, if I believe, and I truly believe, that we're not simply 100-year biological vessels, we're million-year creatures in a billion-year process, how in the world do you frame a question around that? So I take it from my science training. I say, if I'm going to make a work of art, how do I make a work of art that is valid for all inertial frames of reference? That means no matter where in the universe, no matter how small, no matter how large, no matter how long ago, or how far in the future, it's always going to have some sort of operational functionality. Simultaneously, though, my heartstrings are pulled because I'm human. I want to have the sensually engaging evidence that we all do. And so how do you make works of art that sort of frame a question like that, but that are valid not simply for all inertial frames of reference, which is a kind of a quantitative assessment, but is deeply powerful and enriching for who we are, who we were, and who we are to become, right? And so it takes us often out of spaces like galleries and museums. I'm even saying that students in the future, you're not going to be showing in museums, you're going to be opening up space-time and you're going to stick your head in there, and that's where we make stuff. I made light that came from nowhere in the world that anybody knows where it comes from. It's not a picture of it, we're begetting that. So knowing how to frame those questions, taking sort of that large optic, which is making work that's valid for all inertial frames of reference, it kind of sweeps in together for me, sort of the space that I want to work in. And then I inflect through nuances depending on if it's a project like Ralph and I did for a 19th century museum, but still with these expanded notions, then you start using the limitations to kind of work around that. But almost always I frame the questions very large before I get specific.
And because as you were talking, I was thinking more about my question. And the thing for me is that everything you've done here seems like it would be valid and it would succeed in terms outside of art. They succeed as science projects. They succeed as technological innovation. They succeed in all sorts of different metrics. So in what way does defining it as art, what does that do for you in creating it? How does that, what pulls it away from just being the sum of those other realms combined in interesting ways?
More likely than not, I think a few of you raised your hands as engineers. There may be a scientist or two in here. No? Yes? Well, if you have science training and you are a scientist, you would know immediately what I'm doing is not science. It falls in an entirely different domain. It's about discovering what it means to be human and documenting that in a really radically new and enduring tradition. What's interesting, though, and the reason that I receive funding a lot from the sciences, is that in my orientation to my work, I often am willing to ask questions that have such a high technical overhead, that don't have a sort of a genre or a practice-based approach, where I go at this much larger global sort of conceptual orientation, and then I'm fearless, because I have the training my students do, at going into fields that I won't say I don't have background in, but that it's not my precise area of training. You know, we may be able to roll back time 100 years, 120 years, and I might have been a physical philosopher, something different than an artist. But in the, I'll just say the terrain and the topology of the, you know, the 21st century, I fit more comfortably there. The language that I use, the kind of experience that I create, the materials, the process, the thought process, the engagement is always very clearly art. But as I mentioned with system aesthetic, just like taking somebody's image and going in at a level and they disappear, system aesthetic is not just simply being now responsible for every layer and every scale in the universe of your work of art, but it's actually having a practice that's wide enough to where, as I was mentioning earlier, we're training our undergrads for 5 careers. Not consecutive careers, right? But orthogonal careers, so that they're constantly in a process of lifelong learning. And we may change what it means to be a scientist and an artist. If you've got artists who are creating intellectual property that are getting National Science Foundation awards, et cetera, to do speculative research, we may really be on the threshold of doing something different. I sit on the NSF and do a lot of consulting to them, and there's a big push for us to take over the old Carnegie libraries that seem to be defunct in most cities and turn them into maker labs, to where we are reinventing citizen scientists, artists. There's even a push for a national laboratory system like Lawrence Berkeley, like Oak Ridge, but instead of weaponizing things, we actually have artists and scientists working together 50% of the time, allowed to do all the speculative research that they want in any field, and then you get a call on the red phone, right? And there's a serious problem, and minds have to be brought together, and they work very quickly, very efficiently on that, and then they go back to work. And there's sort of a strict dividing line where the call doesn't come 24 hours a day all the time, and all you end up doing is problem solving, because in essence there's a kind of a natural dance between the two of those, so that you can solve problems creatively. You actually have to have time away to do the speculative stuff. So there's significant movement. But yeah, I'm comfortable calling myself an artist, and for the reasons that I tried to describe. And I'm slightly evasive because of being a professor 25 years. I also do things that only open the door enough or cast a shadow for a student to kind of follow a little bit and either challenge me or to stumble into space that, yeah, I can only dream that we'll be in and I'll never be able to make.
Great question, Edward. Other questions or comments? All right, I guess that concludes the evening. You've defied physics once again, though. You packed a 5-hour lecture into 90 minutes.
Yeah.
Thank you very much.
Thanks,
Wonderful.
everybody.